again for the and yeah, thank you everyone for being here. I'll be happy to share some of our recent and ongoing research with you in Separation Science Group at Argonne National Lab. And as you can tell from the group's title, we are working on chemical separations. I like to start with this nice mini review that appeared a couple of years ago, 6 years ago actually. The title was 7 Chemical Separations to Change the World. And one of those separations is rare earth separations. That is the focus of today's talk. And the title was that can change the world, right? But after seeing the movie, Don't Look Up, and I'm going to give some spoiler. If you haven't seen it, you may want to turn off your speaker for a few seconds. There's a comet about to hit the Earth, and then they have the technology to stop the comet, but at some point somebody says, oh, we can extract rare earths from this comet before destroying it, which will be very useful, and it doesn't work. So my point is actually rare earth separations can save the world, not just change. But on a more serious note, there's a National Academy's report that came out also around the same time a couple of years ago, and it emphasizes the importance of rare earth separations and also a fundamental science understanding of separations, because it has been perceived as an engineering issue most of the time, but we don't understand the fundamental physics and chemistry behind the separations, and that is what our group is mainly focusing on. So one of the goals is designing separation systems that have high selectivity, capacity, and throughput. That is the ultimate goal. But to achieve that, we need to understand interfaces and interfacial forces. So that is the topic of my talk today. When we talk about separations, there are many different methods that you can use for separations. They all have different demands for energy. Our group is focusing on these separation systems that require less energy, and especially liquid-liquid extraction is one of the topics that we study a lot. Also, I'll be talking about some absorption membrane type of separation systems and applications. In our group currently, there are 4 projects. Our core program is on lanthanide-actinide separations. This is in collaboration with the heavy element chemistry group. This is a very large program with 5 PIs. And another program is graphene-based materials for separations. And I'll be talking about these 2 topics mainly in today's talk. But in our group, there's another staff scientist, Michael Service. He's leading a critical materials program studying the complex fluids in rare earth separations. And they're using a very unique approach to understand the structures, phase transitions, and aggregation in the complex fluids using critical phenomena. And you will be surprised how many different systems can be easily described by 3D IZ model. So their work is really changing our understanding in the organic phase of liquid-liquid extraction, but it is not going to be in today's talk, obviously. Michael is publishing some papers already. You can check them, and also you can follow his work. And there's another project that we are a small contributor about direct air capture, CO2 capture. We have just started this project in collaboration with Professor May Nyman, but it is not included in today's talk either. Okay, who are we? As I mentioned, Michael Service is a staff member in our group, and Derek, Andy, and Brittany are postdoctoral researchers working with Michael. And Sung-Un and Amanda are postdocs who are working with me. We also had some recent departures from our group. They were postdocs and they found permanent positions. Shirkant didn't go so far away. He joined our sister group, Heavy Elements Group, as a staff scientist. And Raju and Pubudu joined industry at different levels. And I'll be mentioning their work actually because they have done great work in the recent years in our group, and I'll be presenting some of those work. I mentioned that we are focusing on liquid-liquid extraction for rare earth separations, lanthanide, actinide separations. So let me just describe briefly what we are interested in liquid-liquid extraction. In this process, you dissolve your metal ion in an aqueous solution. These lab scale experiments are showing that the colored liquid down here is an aqueous solution of your metallate solutions in this metallate ions in this case. And there's an organic phase on top of it, which is immiscible, and it has some little extractants in it. They are amphiphilic molecules, and what happens is when you shake this biphasic system and let them settle again, they phase separate eventually, but now the metal ions are transferred into the organic phase. And this is a free energy driven process. That's why it requires less energy from outside, like it doesn't need any input. The only energy you consume is to run the liquids. And what happens is the final structure that you are forming in the organic phase has a smaller free energy compared to your beginning for the metal ion dissolved in the aqueous phase. But the molecular scale details of this process, how your hydrated ion comes to this interface, how does it interact with the extractants, and how it is stabilized in the organic phase and form this complex fluid. All this process is poorly understood. We don't know a clear understanding of most of the details here. And our group is really focusing on all aspects of this process. But my personal interest is at the interfaces, especially when the ions are partially dehydrated, interacting with the amphiphilic molecules. How can we understand this process? That will be some of the focus of the first part of my talk. And to understand the interfaces, we are designing some model experiments. We self-assemble some of these extractants at the solid-liquid interface. This is making the system much simpler, obviously taking all the freedom from the extractants, but it is important to get these benchmark understanding before moving to more complex systems. A little bit more realistic model system, we can put some surfactants at the air-water interface representing our extractants, and then we can look how they are interacting with the interfacial water, with the ions in the subphase. So that is another model system that we use to understand these extraction systems. Of course, we also do real solvent extraction, and we look at the organic phases also, and we can compare and find connections between these interfacial interactions and the overall extraction process. To understand the interfaces, we use two major experimental techniques. One is synchrotron X-ray techniques. We do all of our liquid surface experiments at sector 15. We also use some frequency generation spectroscopy to study these systems. This is in our own labs. We don't do the experiments at the same time, but we basically create the same experimental system, and we study with both SFG and X-rays, and combining these information from these two techniques is very important to understand some of the details in these interactions. We also get molecular dynamic simulations in addition to all of these experimental efforts. And since I mentioned the sector 15, this is a nice coincidence that this is my 15th anniversary at sector 15. It was 2007 November, the first time I came to sector 15 for a liquid surface X-ray scattering school, and I loved it. I never left after that. And it was a great way of bringing in new users. Like, I think that's very successful over the years. Postdocs from my group also joined the other schools organized by Benoit and Wei. So I really appreciate everything that Sector 15 did for our research over the years. Okay, so for rare earth extractions, I'd like to give one example. This is a very interesting system. I mentioned there are extractants, amphiphilic extractants in the oil phase that we use for extraction. And they can have all kind of different characters. You can have acidic, basic, or neutral coordinating extractants. Their head group can have very different chemistries. And if you have a positively charged extractant, it is a little bit counterintuitive in the beginning. Like, how are we going to extract trivalent lanthanides using a positively charged extractant? But the fact is, you are actually extracting, in this case, an anionic complex. I show here pentanitrado or pentathiocyanado complexes of rarers being extracted with these quaternary amine extractants. So this is a very interesting problem because we actually don't observe these anionic complexes in the aqueous phase. They are not stable in water, but we know that they're extracted. Number one question is, where do they form? How do they form? That is an open question. And obviously, interface is the usual suspect where this transformation might be happening, but it is very difficult to really catch this during the real process. So it still remains as an open question. But we are also interested in some other interesting parts of this extraction process. And one is your extraction trends depend very strongly on the anion that you choose. So here's the lanthanide series. What I'm showing here is if I choose nitrate as a background salt in this extraction process with quaternary amines, I can extract light lanthanides very nicely, but the trend goes down and I cannot extract heavy lanthanides. If I switch my anion to thiocyanate, this trend completely reverses. Now I cannot extract light lanthanides, but I can extract heavy lanthanides. So that is why we use this this art to describe this process. Lutetium here is trying to choose between nitrate and thiocyanate, and if she chooses thiocyanate, she will be able to go into the organic phase, but if she chooses nitrate, she's going to stay in the aqueous phase. So this is such a dramatic difference. And this is completely challenging to our typical specific ion effects understandings, because in specific ion effects, typically what you have is, as you go down the Hofmeister series, you get more adsorption, less adsorption. There are quantitative differences between the behavior of the anions, especially thiocyanate and nitrate. They are closer each other in the Hofmeister series. You really don't expect a complete reversal in the trend. And that is what is very nice about solvent extraction. It is such an interesting system. It cannot be described with one thing only. It is not a simple adsorption process. There are multiple factors involved determining this complex free energy landscape where your ions are transported from aqueous into the organic phase. When you change your anion from one to the other, apparently we are changing multiple things in this process. And in the competition of multiple factors, we eventually get a reversal in the trend. And it is possible that actually in the presence of thiocyanate and nitrate, the ions are transported through different mechanisms. So that is some hypothesis that we can begin with. Nevertheless, let's start investigating this system. One thing we can do is do the extraction as prescribed. This is a known process, by the way, in the literature. Everybody knows this, but nobody understands why it is happening in that way. So we can do this extraction, and we can look at the organic phase with a small angle X-ray scattering. And we start without any metal ions because we are trying to understand the differences between nitrate and thiocyanate. So let's just contact our organic phase with a nitrate or thiocyanate solution and look what kind of structures form in the organic phase. And it is already very interesting. Nitrate and thiocyanate show very different structuring in the organic phase. Thiocyanate likes to form these aggregates that behave like hard spheres. When I say an aggregate, these are my extractants forming a structure with their tails out and their heads at the center. So the hydrophilic centers and hydrophobic tails in the oil. And they act like some hard spheres. So we see the structures, we can model them as spheres in our small angle X-ray scattering data. But with nitrate, it is not like that. It's completely different. These aggregates come together to form some larger clusters. And even without any metal loading, with nitrate, this is directly happening. So there is a qualitative difference between nitrate and thiocyanate already. So we are on the right path, like we are understanding some very significant differences between these systems. If we extract metal ions, now I am demonstrating the metals with black dots at the center of these aggregates. And what happens is, with the nitrate system, the structuring doesn't change at all. You extract a lot of lanthanum, for example, they go in these clustered aggregates, but the overall structure doesn't change. The increase that we see here is only from the contrast because of the increasing metal loading. We don't extract any lutetium, very little. And again, this is very similar to what we have seen in all cases. The structure is same, but there is no metal extraction. So it seems like organic phase is not playing a significant role with the nitrate system. But in thiocyanate, when we don't extract, the light lanthanides are not extracted, and we see this hard sphere structure that we have seen without any metal before. But if we extract lutetium, now we are extracting a lot of lutetium, and the structure changes. These aggregates now come together to form larger clusters. So the organic phase, the structure is changing in this case. And basically, we hypothesize that this might be the reason of the complete reversal in the system. There are different mechanisms. There is no change in the organic phase, so the selectivity in nitrate system should be determined by the aqueous phase chemistry. On the other hand, there's a more complex process determining the selectivity in the thiocyanate case. So we will be focusing on the thiocyanate a lot because it's a very interesting ion, and understanding its interfacial behavior will be very helpful. As I said, we are now trying to understand these processes and looking at interfaces, what might be the role of the interface, what kind of connections we can get with the organic phase structures and the interfacial structures. One thing we can do is to design a model experiment. We put some model surfactants at the air-water interface, and we change the nitrate or thiocyanate concentration in the bulk, and we study this interface with various methods, including some frequency generation spectroscopy, X-ray reflectivity, grazing incidence X-ray diffraction. And here I show some frequency generation spectroscopy data. But before showing that, let me just mention what we are doing in SFG experiments. We have a picosecond laser, actually two laser beams coming on the surface. One is a fixed 532 picosecond laser, and another one is tunable IR laser. We overlap them at the surface spatially and temporally. Now, and then they generate some frequency photon in a nonlinear process. And this nonlinear process is forbidden in a medium which has inversion symmetry. So, but the interface naturally don't have that inversion symmetry. So our SFG signal is very surface specific. Depending on the structuring at the interface, we are getting very nice information about the interfacial structures. And since we can tune this IR, we can go to different vibrational modes, and we can learn about the structures at the interface. For example, in this case, we are looking at the OH band of water at the interface. So we are trying to understand indirectly how these ions are adsorbing at the interface and changing the water signal. This bimodal signal that you see is very typical at the air-water interface. When you have a surfactant, the charge of the surfactant orients your water molecules, and it gives you a very nice signal at the air-water interface. As your ions adsorb to the surface, they shield the surface charge. Also, they disrupt the hydrogen bonding network of water molecules. So this signal goes down. This is a very typical way of understanding how your ions are adsorbing to the interface. And Very similar to what we have seen in the organic phase, there is a significant, there's a qualitative difference between nitrate and thiocyanate. As you can see, with nitrate, the signal goes down, and that's it. But the main difference in thiocyanate, there are two differences. Number one, if you want to see this bimodal signal, you should go much lower concentrations of thiocyanate. So definitely thiocyanate is much more surface active. So as soon as you introduce your thiocyanate, your water signal starts going down because it's coming to the surface much more strongly than nitrate. That's what we can think by looking at this data. But more importantly, your signal is not just simply going down. We lose only around this 3500 band at low concentrations, and the 3200 band gets redshifted and also gets more narrow as thiocyanate adsorbs. Basically, thiocyanate is forcing a completely different water structure at the interface, starting from very low concentrations. So this translates into the factors that determine the rare earth extraction, because the hydration of these rare earths are very important. How they can bring their hydration shell or how they can lose their hydration shell during the transport is very important, and nitrate and thiocyanate is affecting this differently. And one more note about this data, I love this data really, because when you look at this, we are increasing the bulk concentration of nitrate 10 times from 0.25 to 2.5 here, and the SFG signal is not changing. Now, if we use only SFG, we can say, okay, like there's not much nitrate adsorption at the interface. But when we do X-ray reflectivity from this interface, we see that actually nitrate is coming to the surface, but it is not affecting the SFG signal significantly, possibly because the oxygens of the nitrate is able to incorporate, it helps them to incorporate themselves into the hydrogen bonding network without disrupting it that much. So this is a very interesting observation. It is important in terms of the behavior of the ions at the interface, and also it is important when we are interpreting our data. SFG data by itself, especially looking at the OH region, may not be very, it may not be correct to understand the ion adsorption in an indirect way. So we should look with different probes to this interface. That is very important. And that's why, like in our group, we really emphasize using surface X-ray scattering and SFG spectroscopy together. We use a more, let's say, controlled image on a journal cover. I would use this one if you ask me, but probably you cannot use a meme. But anyway, so at least this describes our approach in a better way. So let's try to use all the probes we have to understand the system a little bit better. And to do that, instead of thiocyanate, we introduced selenocyanate, because selenium has a very nice X-ray absorption edge. It is very similar to thiocyanate in its behavior. So we can use X-ray fluorescence to understand the ion adsorption at the interface, and also use all other probes that we have been using. Especially with the SFG, we can also look at the CN stretch, and now we can compare what do we see with X-rays and what we see with SFG, and it will give us a better understanding of all the behavior at the interface. This is our fluorescence data. We are we are increasing the selenocyanate concentration in the bulk, and from the fluorescence, we can determine the coverage of these ions at the interface. I'll show the results in a bit. This is our SFG experiments. We can look at the CN stretch, as I mentioned, and we can do it in multiple ways. We can control the polarization of the laser, and by choosing different polarization combinations, you get sensitive to different orientational ordering in the SFG. And that's the tricky part. SFG is not only proportional with the number density, it is also sensitive to the orientational ordering. By choosing different polarization combinations, we can resolve basically how the orientation of these thiocyanate molecules are changing at the interface. For example, in this PPP polarization mode, we see that the signal is very strong and it keeps increasing with the increasing bulk concentration. But with SSP polarization, we pretty much don't get any signal. And SPS is giving a stronger signal compared to SSP, but weaker than PPP. And its trend as a function of bulk concentration is also different, demonstrating that the orientation of these molecules are changing as a function of the bulk concentration. And when we combine this information with the fluorescence data, we see something very interesting. The blue dots here are showing the coverage that we get from fluorescence experiments. And what we see is at very low concentrations, around 0.1 millimolar, actually the surface concentration is saturated. And we need to remember here, our fluorescence is probably probing 5-6 nanometers at the interface. So we are saying that the total number of cyanide ions in that region is saturating. So that includes the stern layer very close to the interface, and also the diffuse layer. Basically, we are counting all of those ions, and their number is saturating at very low concentrations. But the PPP signal keeps increasing. That is suggesting us this increase is not from the increase in the number density of the cyanide, but their orientation is actually getting more parallel to the surface normal as the concentration increases. And also we have reflectivity data, GID data on these systems. And by combining all of that information, here what we think, at low concentrations, we believe most of the ions are actually adsorbed in a way that they are not directly interacting with the surfactants. So this is at very low concentrations. And when they are not very directly interacting with the surfactants, their orientational ordering is a little bit more distributed. So that is why this PPP signal is not that strong at that concentration. So the total number is not changing from 2.5 to 25 millimolar, but what we think is there are more ions getting from stern layer from diffuse layer into the stern layer, and they get more parallel to the surface normal between these two concentrations. That's why the fluorescence is pretty flat, but the PPP signal keeps increasing. And now one interesting observation here is this SPS polarization combination looks like it is following the fluorescence signal. So it seems like the SPS is less sensitive to the orientational ordering or the orientational ordering changes that we observe in the system, and it is pretty much correlating with the number density. This is just an observation. We're still trying to do develop a better understanding why it is exactly happening in this way. Now, if you see that, like, our experiments here ends around 100 millimolar, but we in separation systems, actually we work with much more concentrated solutions. So now we want to study higher concentrations. It looks like it is saturating at this point, but what happens if we go further? Very interesting observations we have with the SFG system when we increase the concentration up to 5 molar. Now I'm going back to thiocyanate because cyanide is not that soluble, so thiocyanate is better to work with at this point. And again, we are looking at PPP and SPS polarization combinations using SFG. And after this saturation, what we see is the PPP signal starts going down, and SPS signal goes up and then stabilizes again. This is very interesting. Again, the signal is not only proportional with the number density, but also orientational ordering. And if you have two thiocyanate ions oppositely oriented, their signals will cancel each other. Is that what is really happening with this PPP signal? To understand that, we cannot understand it from this classical SFG measurements, because we lose the phase information. Very similar to our X-ray experiments, there's a phase problem, and when you lose the phase, you cannot understand the orientation. But we can solve it in SFG by using phase-sensitive SFG experiments. And here I just show briefly how phase-sensitive SFG works. This is a classical SFG experiments where you use two lasers and get your SFG signal. In phase-sensitive, we generate some frequency signal from a Y-cut quartz, and then we generate another some frequency signal from our sample, and we interfere them by controlling the delay between these two signals, and that interference allows us to determine the phase from our sample, and basically it gives us the information about phase information and the orientation of these molecules. So just to pause for a second, I like thinking memes, and yeah, our phase-sensitive SFG can see everything up and down, and classical SFG cannot see that. And our hypothesis about why that PPP signal was going down with increasing bulk concentration was actually correct after studying the system with phase-sensitive SFG. Now we can measure the imaginary Chi2 directly from phase-sensitive measurements, and what we see is this negative peak corresponds to a new population appearing with the opposite orientation. And as you can see, this is happening right after 1 molar concentration when we start seeing the decrease in the classical SFG signal. And very interestingly, the peak position for this down-looking thiocyanate ions are different than the up-looking ones. And it is suggesting that the coordination environment is different for up-looking and down-looking thiocyanate molecules. And Michael and PSEUDO did some MD simulations confirming the overall picture here, but it is a little bit more complicated than what we can just understand from the SFG experiments. So our studies are going on with this, and we're hoping to get a better understanding of the system with the help of MD simulations. Okay, so I'm running a little bit low on time. That's why I want to skip some parts that I couldn't mention in the previous part. But let me move on to a little bit different topic about graphene surfaces, graphene oxide surfaces, and heavy ion or rare earth adsorption on these surfaces. Different than solvent extraction, the target of these studies is more membrane type separations or capacitive deionization. For example, graphene might be a very good electrode for capacitive deionization. So we are trying to understand how heavy ions interact with these novel surfaces. One experiment I'm going to mention is trivalent ion adsorption on electrified graphene. And so what we do is we have epitaxial graphene on silicon carbide, excuse me, and we apply a potential. We have a trivalent yttrium solution in our sample cell. Here is the real sample cell that we use at sector 33, and we look at the surface and how ions are adsorbing and how water is behaving at that interface. Again, our goal is to also complement these experiments with some frequency generation spectroscopy experiments, but I'm going to show mostly X-ray data here. We can do 2 different experiments at this interface. Yeah, excuse me for a second. And one is X-ray reflectivity, or since we have a crystalline substrate, we can do crystal truncation rod measurements, high-resolution X-ray reflectivity. Also, we can tune the X-ray energy around yttrium absorption edge, and we can do resonant anomalous X-ray reflectivity to determine the ion position directly. This is a very great advantage that we have at APS. Now, our crystal truncation rod measurements show some differences, and when we fit this data, what we see is we can get the electron density profile at the interface. Here is our graphene, and this is the water. Like we show in different colors because, and this is just graphene in water, and then this is 10 millimolar yttrium chloride, and we are applying a negative potential to the surface. Now, we see some structured water at the interface. Here we represent these with different color because they appear like a different adsorbed layer. A little bit more persistent than your typical water. This is very well known, like you can see structured water on mineral surfaces, also on graphene. This has been observed before. But what happens is when we apply potential and introduce yttrium, there are very significant changes to this interfacial water structure. And it is not clear directly how much of it is coming from yttrium. And that's where we need resonant anomalous X-ray reflectivity. And with the Raxer measurements, what we do is we are tuning the energy at a fixed Q. We go to a fixed reflection, and then we are changing the energy, and basically we are doing an energy scan around the edge. And by looking at how the phase of the resonant between the resonant and the non-resonant signal, we can determine the position of the ions from the surface and also the coverage directly. And I'm just showing some representative data of Raxer from graphene interface. And as you can see, by scanning different Q values, different reflection angles, we can see a very clear phase change, and that helps us to determine the coverage and the position of the yttrium ions at the interface. And the results we are getting are very, very interesting. Number one, most of the structuring that we see, it is not directly related with the yttrium. The yttrium distribution is shown with this orange line, and it is a very diffuse profile, unlike most of the adsorption that is observed at the mineral water interfaces. By the way, we do this in collaboration with Sengsoo Lee in Paul Fenter's group, and they have been studying the mineral interfaces for a long time. And this is very different compared to what you observe on a typical mineral surface. And the other interesting thing is the concentration of yttrium is significantly higher than what you would expect, what you could estimate from a cyclic voltammetry measurement, for example. A CV measurement would tell you the interfacial concentration of yttrium is around 0.1 molar. Remember, our bulk concentration is 10 millimolar. So this is already a high concentration that compared to bulk estimated from CV. But our Raxer measurements are actually saying that we have 20 times more yttrium close to interface that we could estimate from the CV measurements. And of course, CV is only measuring the total charge, and there will be anions accompanying the yttrium at the interface. So that is how you get the charge balance. But still, bringing that much yttrium to the surface, but not able to get them very close to the surface, is a very interesting observation. And that is an important property of the graphene, because this is a pristine graphene with no functional groups. And therefore, there's no way for these yttrium ions to coordinate at the interface. That is probably why they are adopting this interesting distribution at the interface. And we are now working on the system. We had a beam time recently, so we are getting more interesting results about this system. Hopefully, next time we can talk about that. But now, in the last minutes, I would like to move on to a little bit different topic. Not different. So this is pristine graphene, and I said like the absence of the functional groups is causing maybe this interesting adsorption behavior. We can go to the other extreme of a graphene-based material, which is graphene oxide. And graphene oxide is derived from graphene, and by creating various functional groups, by oxidizing it, obviously, creating multiple functional groups. And the dominating functional group is carboxyl, mostly on these systems. And we would like to understand how ion adsorption would happen on graphene surface. And to be able to do that, we try to self-assemble graphene oxide at the air-water interface. That is the best way to create a thin film of graphene oxide and study ion adsorption on that. And we do these experiments again at sector 15 using X-ray reflectivity, X-ray fluorescence, and we also do some frequency generation spectroscopy experiments. Here in this study, we are comparing monovalent, divalent, and trivalent ion adsorption. There is a significant difference when you adsorb trivalent ions to these graphene oxide films, because unlike monovalent or divalent ions, trivalent ions change affect the graphene oxide structure. So we are observing that those changes using X-ray reflectivity. But this first study was very difficult. We had very hard time getting stable and reproducible graphene oxide films at the air-water interface. It wasn't very easy. And one reason is graphene oxide is not a perfect amphiphilic like the other surfactants that we are using. It has some amphiphilic character, but when you're spreading, it is very possible that maybe some of graphene oxide is dissolving in water actually, and therefore creating a nice film is not easy. Also, depending on your functional groups, as you change your graphene oxide, you might be creating a different film. So we need some universality in creating these thin films. And Amanda and Raju spent quite some time on this, and finally they developed a method to prepare these graphene oxide thin films in a very reproducible way by using very little amounts of graphene oxide, minimizing the graphene oxide dissolution in water. And this basically includes some sonication in methanol and then filtration. And we have described it in this preprint if you're interested, but I won't go in details. I will just show one data that we obtained with this system. With this high quality films, now we can look at the graphene oxide water interface very nicely using SFG and reflectivity again. And here we see something very interesting as we adsorb yttrium to the graphene oxide surfaces. We are increasing the bulk concentration. You remember this, like these bimodal peaks from my previous data. That's what you see at the air-water interface if you have some charged film on the water. And then that signal goes down as you adsorb ions, again, shielding the surface charge and also disrupting the interfacial water structure. But very interestingly, there is a very high frequency peak here in the graphene oxide system, which doesn't change. It is not affected pretty much from the ion adsorption. And we believe this is some water coordinating directly to graphene oxide or trapped between graphene oxide layers. And this is very important in membrane type applications, because how your ion interacting with your membrane material is also determined with the presence of other water molecules around, and we are showing that there's a persistent water layer on graphene oxide, independent of the ion adsorption. And controlling this water will be very important for membrane applications. So I think I'm at my time. I don't want to take longer, so I'm going to skip this and come to some conclusion. The separation systems that we are working with, especially with trivalent ions, and I couldn't even talk about any actinides, but we know that their behavior at interfaces are very different than your typical Guy-Chapman theory monovalent ions. They are point-like. You can assume your water is just a constant dielectric background. The real systems that we are dealing with, they are very, very different from that. So the multivalent and complex ions at interfaces, I think, is a very interesting topic. And separation systems can provide very interesting fundamental science questions to all the surface science community. So I just list some of those questions here. And I'd like to finish with a little advertisement. I'm organizing a session in APS March meeting this March 2023 about this exact topic, multivalent and complex ions at charge interfaces. If anybody is interested, please submit an abstract. The deadline is this Friday. And with that, I'm just skipping this talk and coming to my acknowledgements. Yeah, thank you all the separation science group, heavy elements group, as I mentioned. We are collaborating a lot, and our other collaborators include Aurora Clark from University of Utah, Sang-Soo from Interfacial Processes Group. We are using multiple beamlines, and all of our funding is Department of Energy, Basic Energy Sciences. Thank you for your attention.